So if you didn't get a chance to work the problem, make sure you have pen and paper out, and then we'll just kind of go through it. They've already done the conversions for us. They've already given us the voltage in phasor form. They give us the reactance and resistance. They don't provide the angles. Of course, we have to supply those when we do the calculations. So if you have the sheet, kind of just follow the steps on the sheet. And the first thing they want us to do is to find the total impedance. So you might think, okay, how do I do that? I know if I had a series circuit, to find the total opposition, I would add up all the individual oppositions. Well, here, what you would do is you take the same approach that you would take as if this were a DC circuit. You can do that. You're allowed to do that because a phasor is an RMS value. You can treat it just like it was DC. So if this was a DC circuit and you were asked to find the total resistance, you use the 1 over R rule. We'll use the 1 over Z rule. So I'll write the formula down and you guys can help me calculate. So the total opposition, the total impedance, 1 over Z. And remember what I said last time, 1 over Z, it's called the admittance. 1 over Z is the admittance. You said 1 over R, that was the conductance, and then 1 over X, that was the susceptance. They used a B for that. So we find the admittance over here, and then we'll invert that. And so if I want to do that, I just go 1 over the first branch, which has a resistor in it, 1 over the second branch, which has an inductor in it, 1 over the third branch, which has a capacitor in it. So we'll supply the numbers there, we'll calculate it, and see what we come up with. So for R, we got, what, 3.3 ohms? Put that in there. .33 ohms. I'll leave the units off just for room. We got 1.43, and then we got 3.3. Just like you would as if you had a DC circuit, exactly the same. So if we do the math, I think for that first ratio, I actually worked this out. I got 0.3. Now, that resistance is at an angle of 0 degrees. So when I bring it up, it'll still be at an angle of 0 degrees. So you just kind of, if you actually work this out, just kind of see if this agrees with what the answer you got. 1 over 1.43. I got, now that's a, well, that would be, I got about 0.7. I guess I can round it to 0.7. But this angle here, that angle here is, since it's a inductor, that angle is a positive 90. So when I divide it, the angle comes up, it'll be at a minus 90. And then this, I'll get the same, the 0.3. This angle associated with this is a minus 90. So when it comes up, when I do the division, it comes up as a plus 90. So that all equals 1 over Z. So I can just add these up. I can add these up directly without converting them over because, well, I know that's a 0.3. I know that. So I got 0.3 angle 0 degrees. But these two right here are on the same line, right? So one is at minus 90. So one is like this. One number's polars pointing down like that. The other, this is minus 90, and it's at 0.7. So if you just think of that as an arrow pointing down, negative 90, and this is pointing the other way, that way, it's only 0.3 magnitude, it's pointing up. So I'm going to take the difference between those, and I'm going to get a plus 0.4 in the direction of the bigger complex number, which would be an angle of minus 90. So kind of look at what I did, make sure that makes sense. when we do the divisions, this is what I get. Remember, that is not Z, that's 1 over Z. So all that's equal to 1 over Z. That is basically Y. That's Y. So now what I got to do is convert this to rectangular form. So we'll convert that to rectangular form. Let's see. If I convert that to rectangular form, I get a 0.3, and then my 90 degrees means I have a minus J, and then I have the 0.4. Now my angles, remember that's Y, that's 1 over Z, so this is actually inverse ohms. That is equal to 1 over Z, which is equal to Y. So there it is in rectangular form. And then if you can take this and convert it over, you convert that over to polar form, so you end up with just one number. What you end up with, or what you should have ended up with, if my math is correct, you should have ended up with, if you convert this over, so do a rectangular to polar conversion, and I ended up with 1 over Z is equal to 0.5 at an angle of minus 53.1 degrees. So that's our admittance, but I don't think we have to find admittance. Nope. That's our admittance. They asked for the impedance, so I just got to take this and invert it. So Z is 1 over Y. If I take 1 over that, I get 2 at an angle of 53.1 degrees. So there is my impedance, using the formulas, same formulas that we will use for DC. So hopefully you got that to work out for you. That's the first question on the sheet. Calculate the impedance. So I'm just going to stick this up over here on the side so we have it. So Z equals 2 angle 53.1. Okay, so we got the impedance. And then it says draw the admittance diagram. We talked about the impedance diagram, I believe last time we were together. What is this thing called, with a parallel circuit, there's this thing called the admittance diagram. I don't really like working with admittance diagrams, but I mean, we could do it. What you want to do basically is just graph this. Let me put both diagrams up so you can compare one to the other. So you know, let me see, I think I can get rid of all this stuff. I hope I can. So we talked about the impedance diagram. So if you remind yourself what that looks like, the impedance diagram looks like this. This is resistance, this is XL, and that's XC. That's the impedance diagram. For the admittance diagram, this would be G. Now, if you remember, 1 over X is equal to B. So 1 over XL will equal BL. But on this admittance diagram, you're going to reverse the position of the inductor and capacitor. So 1 over X is B, 1 over XL is BL, but what I'm saying is you're going to put the BL down here at the bottom. If you remember when we did that division, when we divided, this was at an angle of 90 degrees. When we divided it, the angle became negative 90. That's why that flips. And the same for this. So this would be BC. And then what you could do is just kind of graph this. I go over 3 on my inductance. So I'm going to go out 3. I'm just going to kind of guesstimate it. So I go over 3 like that. Then we'll go down 4 units on my, this is my minus J here, my plus J. So I go down -4 that way. Again, I'm just estimating. So this would be G, and this would be BL. And then to get your admittance, you just make a triangle or a rectangle out of this, where you have a 90-degree angle there. And to get the admittance, you just start at the origin and come out to the diagonal corner like that. So that right here is Y. And you remember Y, this is Y right here. So it has an angle -53 degrees. Well, that's this angle right here. That's your admittance angle. I mean, I could ask you to do that when I give you a quiz on this stuff, but this is important to me, impedance diagram. If you know this, you should be able to get to this if you wanted to. So I don't know what it is, but I may not ask anything about that. So that's number 2 on the sheet. Number 1 was find the impedance. We did that. Number 2, the admittance diagram looks like that. Now they want you to find the total current. So how would you find the total current? Again, you would act like this was a DC circuit and a DC parallel circuit. And in DC, if you want to find the total current, you'd have to know the voltage. You have to know the opposition or the resistance. And in this case, we know both of these. They give us the voltage. So the current phasor, it is a phasor. The current phasor is equal to the voltage phasor over the impedance, which is not a phasor. So if I have 100 angle 53.1 degrees volts divided by my impedance, which is this. This is 2, has the same angle, 53.1 degrees ohms. When I divide that, I'm going to get 50 at an angle of 0 degrees, and my units would be amps. So my total current looks like I got 50 amps of current flowing in that circuit. So just like you did in DC, what I would do is just show that as the main line current coming up around here like this. And then we'll write it as 50 angle 0 degrees, and the units will be amps. So again, you see why you want to use your coloring pencils and pens and all the stuff that you use when we did this stuff in DC. Things get kind of complicated on your diagrams. So if you're going to submit that, it's easier to find out what certain values are if they're color coded. Okay, so we found the impedance. We found the current. Next, he wants us to find, it says find each branch current in both polar and rectangular form. Find each branch current in both polar and rectangular form. Okay, well, the polar will be easy. Then we got to convert it over to rectangular. So the branch currents here, there's 3 branches. So let me make sure I don't need this anymore. I think I'm probably all right. So we want to find the branch currents. So I want to find the branch current through the resistor, branch current through the inductor, and the branch current through the capacitor. And those are all phasors, so I got to do this. And that branch current, voltage is the same in the parallel circuit, so it's just E hat on R. This is E hat on XL, and this is E hat on XC. So put the numbers in there, and we'll do the calculations. 0 degrees, R is 3.33 angle 0. And this is 100, 143, right? So positive 90. I'm leaving the units off, so you guys should write the units. And this is 100. And this is angle minus 90. So that should get us our currents in polar form. And if you do the math, I think I worked this out. So you check yours against mine to make sure I did it right. For this one, I got 30 angle. Wait a minute, I got something different here. Oh, this right here, I said I made a mistake. This angle here is actually 53.1 degrees. So I wrote that wrong for all of these. I'm surprised you guys didn't catch me on that. It should be 53.1. So if you're writing this down, make sure you change that. I think because I didn't write it on the side, I just didn't pay attention to it. So now this would be, yeah, that looks better. So this would be at an angle of 53.1 degrees, and the unit would be amps. Now, if you look at this, this is the current through this resistor right here. So look at the phase on that current. It's 53.1 degrees. Look at the phase on the voltage across the resistor. It's also 53.1 degrees. Remember what we said. I'm trying to emphasize this a couple times. The voltage across the resistor is always in phase with the current through it. So if you had done that calculation and you got two different angles, that's kind of what made me say, oh, I must have made a mistake. If you got two different angles, then you know something's not right. The angle for the voltage and angle for the current should be exactly the same if we're talking about a resistive component, a resistive element. For IL, I got this one, I got 70, angle minus 36.4 degrees. And then on the last one, we got 30 again. But the angle this time is 143 degrees. So there are all my branch currents. And, you know, you could actually probably should just write these right here. So I'm going to write it right here. So that one right there was 30 angle 53.1. 70 angle minus 36. And that's a 4. And the last one, 30 angle 143. So there are all my branch currents. Now he wants us to, I don't think I converted these over. He wants us to, he says to show these in both polar and rectangular form. And I didn't, well actually I did. Well, I guess we can go ahead and do it. You can convert them over. Check me on my math on this to make sure I did it right. When I convert this, this will be my polar to rectangular. Let me change the color of the marker so it's easier for you to see. So I converted those over, and if I did it correctly, I didn't use a calculator. I mean, I used a calculator, but I didn't do the automatic thing where it converts automatically. This one I got 15 plus J24. This one I got 56 minus J42. And this one I got minus 24 plus J18. So that's what I got when I convert it. Now, why do they want you to convert it? Well, the reason they want you to do that is because they want you to show that Kirchhoff's current law is valid for this circuit. If you remember, Kirchhoff's current law says that the total current should equal the sum of the branch currents. And so you can't add those in polar. You got to convert it over. So my total current, let's see if I converted the total current. Yeah, my total current, this, when I converted over, what I got when I converted it was 47 plus J0. So if you did this, compare this to what you got, make sure I'm okay. If I add this branch current, this branch current, and this branch current, hopefully this adds up to something close to 47. And let's see, I got, yeah, this adds up definitely to 0. That gives me a 0 because this and this is that. So I think we're good. Now, I don't really care if you do this or not. I just, if on a quiz or at some point, if you have to prove KCL, if you have to prove Kirchhoff's current law, this is the way you would do it. You convert all the branch currents to rectangular, add them up, convert the total current to rectangular, and compare the two. And if they compare favorably, if they're equal, then you've proved Kirchhoff's current law. So that was the point of doing that. So if you did it, fine. If you didn't do it, it's no big deal. So that would be number 5 on the sheet. Now number 6, I want you to draw the phasor diagram. So remember, the only thing that can be a phasor is a current or a voltage. So they want us to draw the phasor diagram. And that should be, we got all the information here. We can do that pretty quick. So let's draw the phasor diagram. So in the phasor diagram, I will show my total voltage and total current. My current is at 0 degrees. That's kind of my reference. So I'm going to show my current right here. That's my total current. My voltage is at 53.1 degrees. So it's up in quadrant 1. And it's a magnitude of 100. So my voltage is kind of like this. We call it E, don't we? E. Now notice, before I put my other phasors on here, I'm looking at my total voltage and my total current. The angle between these two is at 53.1 degrees. So that angle, that's this angle right here. That's this. But as I said last time we were together, these phasors, even though I can't show it here on the board, the phasors are actually rotating in a counterclockwise direction. And here's my voltage phasor, and here's my current phasor like that. So we take a snapshot of it, which is what the graph represents. It's actually rotating like this. And that phase angle at 53 degrees, they stay 53 degrees apart. And if this is your eyeball looking at this, say you're looking right here, here's your eyeball. What you would see my voltage phasor go by, because you always look through the smaller angle. My voltage phasor will go by, and then my current phasor will go by. So what's that mean? That means the current is lagging. So current lags. Let's put that up. IT is lagging. Now, why would you need to know that? Well, remember when we do power, I don't know, you may not ask us for power factor, but later on, if we need to find the power factor, I got to write it in terms of the current. The power factor is either leading or lagging, and we define that leading or lagging as whatever the current's doing. So in this case, the current is lagging. So if they ask us for power factor, it will be a lagging power factor. All right, so that's my my phasor diagram. And what you really should do on this is show all the phasors. So I'm going to show these other ones, and I'm going to make it a different color just so they stand out. So I got my current through my resistor is at 53 degrees, which sits on right on top of the voltage, and that should be that way. Remember, the voltage and the current through the resistor are always in phase, so those two phasors are riding right on top of each other. I got my my current from my inductor. It's at minus 36 degrees. So let me use the blue marker. So my inductor's in quadrant 4. So it's like this. That's IL. And look at this. This is 30 angle 143. So this is actually, I drew this like an impedance diagram. In your phasor diagram, you actually have the axis right there. But the point I was making is that if you know where this is, then you know where IC is, because they're always 180 degrees apart. If you look at the angle between 143 and minus 36, you'll see it's 180 degrees. So these two currents are always 180 degrees apart. You'll always have this angle right here of 180 degrees. So once you locate one of those, the other one's easy to get. So there is my phasor diagram. Now here's a case where if it's a series circuit and you want to see if the current's leading or lagging, you can kind of just look at the numbers. If the capacitor is bigger, it's going to be, you can use Eli. If the capacitor's bigger, the current's going to lead. If the inductor's bigger, it's going to lag. But when you have something like this, it might be a little harder to see. Well, the best way to see it on the parallel circuit, if the numbers don't tell you, is to just look at the phasor diagram. And notice I grabbed the total current and total voltage first to see which one was leading, which one was lagging. And once I got that information, then I put the other phasors on there because I knew this thing was going to get crowded. All right, so if you look at the sheet, that's all the problems, the parallel problems. It was 1 through 6. But now if you look at 7, this is more power stuff. Last time we were together, I introduced AC power. Well, we just really introduced it because it's way more involved than what we talked about so far. But this takes you through the same kind of logic. So we'll go ahead and we'll look at this. So it says calculate the total power using PT equals E times I times cosine theta. So I showed you in the last class that you can find the power delivered or power dissipated by using that equation. The power delivered, I'll just call it PT, is equal to E times I times the cosine of the angle between them. And remember, I don't show the hats on these because I'm not interested in the phasor part of them. I only want the magnitude. And these have to be in RMS. This right here, that cosine theta, remember we call that the power factor. And I also talked about the cosine being since it's an even function, even though we know the angle between the two is 53 degrees, if I put a negative 53 in there, I'll still get the right answer because that's an even function. If I do the math, I have E, which is 100 volts, and I, which is what, 50? You're 50 amps. So, and then the cosine of the angle between them was 53.1 degrees. And then so when I did my calculation for that, let's see what I got. I ended up getting 300 watts. I ended up getting a total power of 300 watts. So again, you check me on the math, and I think what I did was correct. So what we did again, we used this formula right here to get the total power. Either you can say the total power dissipated or total power delivered. And the reason I'm phrasing it like that will become clear when we talk about power. I don't know, might be, I have to see where we're coming up on it where we need to talk about AC power. So that right there is number 7. Tells us to calculate the total power using this formula. But then he wants you to do the same thing. Remember that conservation of energy thing we talked about last time? He wanted to show that the total power is equal to the power dissipated by the resistor plus the power dissipated by the inductor plus the power dissipated by the capacitor. We want to show that that is a true statement. So I'll get rid of this. And I think I can get rid of all this because I got these up there. So what he wants us to do is to show that the total power is equal to PR plus PL plus PC based on this EI cosine theta. So we're going to write this for each term. Now we already got the left side. We already got that. We know that that's 300. So I'm going to go ahead and put that over there. This is 300 watts. What we want to do is to show that the right side is equal. So if the total power is equal to the total voltage times the total current, then the power for the resistor is going to equal the voltage across the resistor, which is just E because it's a parallel circuit, times the current through the resistor, times the cosine of the angle between these two. Now remember, when I have a resistor, they're in phase. And we said last time when we talked that if you remember, the cosine of 0 degrees is equal to 1. So basically, this right here goes out as 1. So my power dissipated by my resistor is just equal to the voltage times the current through the resistor. So let's see what that is. Well, the voltage is 100 volts. And the current through the resistor is 30. And that is 3,000. Now, I got 300. I wonder if I made a mistake for my math. Or did I just drop a 0?
I think it's 3,000. I did the same thing. I was kind of wondering where you came up with that 300 at.
Okay. Thank you.
No problem.
All right, so this is 3,000.
Yeah, I did it 3 times and I was confused.
Yeah, I just need to admit I'm old now and I need glasses is what it is. So we got 300 right here. Now already look at what this is telling you. That the resistor is dissipating all the power. Okay, what about these two? Well, let's look at what the math tells us about those two. So for this right here, if I write the formula for power for PL, the power for PL is going to equal the voltage across the inductor, which is just E, times the current through the inductor, which is IL, times the cosine of the angle between these two. Now, if you remember, the angle, remember Eli the Iceman, whether I have an inductor or a capacitor, with an inductor, this tells us which leads and lags, right? With an inductor, the current's going to lead, the voltage is going to lead, the current's going to lag. For a capacitor, the current is going to lead, the voltage is going to lag. But the phase between them is always 90 degrees. So no matter where I have this one or that one, the phase between E and I is going to be 90 degrees. And if you remember what we said, the cosine of 0 is 1. The cosine of 90 degrees is 0. So look what's going to happen. When I do the math here, this cosine is going to become 0. And 0 times no matter what this gives me is going to be 0. So PL, both PL and PC are going to be 0. So this right here goes out to 0, and this goes out to 0. The math is telling you that the only thing that dissipates power in this circuit is the resistor. The inductor and the capacitor, they cannot dissipate any power. Now we're talking ideally. An ideal inductor, a perfect inductor, it's impossible for it to dissipate power. An ideal capacitor cannot dissipate any power. And again, we'll use that when we talk about AC power. We'll talk a little bit more about that. But basically, here's the way I think about it. This dissipates energy. It takes energy, it acts as a transducer. It takes energy in electrical form and converts it to heat. A transducer converts energy from one form to another. A resistor converts energy from electrical energy to heat energy. But the inductor and the capacitor, think of them like a spring. You can stretch a spring or you can compress a spring. So what a spring will do is if you stretch it or compress it, it will store energy. And when you release it, it'll give you that energy back. So think of these as kind of electrical springs. Energy comes in, the energy goes back. So this will dissipate the energy and change it to heat. This will borrow the energy for a while, run into the inductor, and in the inductor, the energy goes out into the magnetic field. When that magnetic field collapses, the energy is sent back to the generator. And here, the energy runs into the capacitor and is stored between the plates and the electric field. When that electric field dissipates, the energy goes back to electrical energy and goes back to the generator. So the reason they wanted you to do this is to see mathematically, the math shows you that it's impossible for an inductor or capacitor to dissipate power. The math is showing you that. And again, we'll get more into the details of that when we talk about power, which I got to see. I think that might be the next thing we're talking about. I got to look and see. All right, so that is problem number, which one is that? Number 8. And number 9 says, the fact that this is 0, PC is 0, PL is 0, what does that imply for PL and PC? What does that imply for the inductor and the capacitor? Well, it's what I said. Reactive elements do not dissipate any power. Reactive elements do not dissipate power. So that's the thing to remember, the takeaway. And then the last thing here, they want us to show the power factor. Well, power factor is just this part right here. And we already kind of know what number it is because it's just going to be the cosine. What we said we're going to use for power factor. Some books use this. Some books use this. And I just do that for power factor. So for power factor, it's just the cosine between the total current and total voltage. And so we know the angle between them was 53 degrees. And when you do the math, you get 0.6. But now you got to see, is that power? If you just write 0.6 on a piece of paper and turn it in, you get it wrong. You got to say if it's leading or lagging. Remember before when we looked at the phasor diagram, we determined that the current was lagging. If the current's lagging, then that means the power factor is lagging. If the current was leading, then that would mean that the power factor is leading. We always define the lead or lag on the power factor. Whatever the current's doing, that's what the power factor is doing. And again, I mentioned in the last class, what information does power factor give us? Well, I mentioned towards the end of the class where the higher the power factor, the more resistive the circuit. The lower the power factor, the more reactive the circuit. Now, you don't know the importance of that, but when we talk about AC power, you'll see why that's important. So there's a parallel circuit. We've done, I think we did 2 series circuit practice problems, and we did 1 parallel. So does anybody have any questions or comments on either the series or parallel calculation? It should be pretty straightforward because it's exactly what we've been doing in DC. The only difference is you got to do this angle stuff. But once you get that under your belt, it should be a piece of cake. You can't drop zeros from your powers and all that, but it should be all right. So anybody have any questions over anything? Everything pretty clear? You know, I don't know why I'm looking at this computer and Randall, who's that? Yeah, Randall's icon is different than everybody else's. I don't know why. I noticed that every time you log in, your icon is, I see Jacob, and then I see, is it Brandy, Tresser, and Dominic must have dropped out, and I have one person calling in. But it's funny because everyone else's icon, the person is black, and the circle is white, but on Randall's, the circle is like gray and the icon is black, or white, I'm sorry.
Maybe because I log in through Blackboard, they may take the link that you gave them. That's the only thing I can think of.
Okay. Maybe so.
I don't know.
Yeah, I don't know.
You know, mine is different for different classes too. Mine looks like Randy's in my math class and my programming class. Mine only looks like this in your class.
Really?
Yeah, but I think I always click your link to come into this class just because it's right there. And then the programming and the math class, I just go through the little collaborate button.
Well, that's what Randall said. That's probably what it is then, since you click the link. So all the link clickers, they make one icon. They make it. That's kind of cool. I kind of like that. I can tell how you clicked in. All right. Well, let me get rid of this, and we got one more to talk about, series parallel, and then we can get rid of this stuff. I'll give you a packet of practice problems to do. I got a packet of. I have a work solution. I got a problem, and then I got the whole complete work solution that you can work through and make sure you got it. And then at some point, you got to show me that you can do this. Since you're doing it at home, you're going to have all the equations right there. I don't know. The quizzes are kind of silly to me because you got everything right there, but you do have to show me at some point that you can do this, so we'll figure that out.
I
think I mentioned it. Was it about this?
I mean, it's about everything, kind of. I was curious. I think I missed when do we put the unit in brackets versus when do we just write the unit straight up?
Yeah, so that's the meeting. I did that. So here's what they do. They do. Let's say you have a voltage of 100. Most books will do this. They'll have 100 volts, angle maybe 36 degrees. I don't like that. I don't like the way that looks. So then some people will do 100 volts. They'll say theta equals 36 degrees. That looks better than that to me. I did that just. So I'm the one that made up this 100 angle 36 degrees, and then just show that that's volts. So you know that that is a. Anytime you see a square bracket, that means it's a unit, and it's not like the V equals or the I equals. So what I do here, just to make things, since there's so much writing and things get so cluttered, to make the unit stand out, I put brackets around it. And to make the quantity stand out, I use a certain color for voltage, a certain color for current. So this is a me thing. I don't think it's standard in any book or anything. I might have found that in a book or something over the years. I don't remember where I got it from. So if you were to leave that off, I wouldn't mark it wrong. I mean, if you just wrote volts there, as long as you got the numbers right, you're good to go. So, yeah. Okay, so let me show you if you guys remember when we did series parallel in DC, if we have given a circuit where we know all the values, what we did was we identified the nodes and we condensed the circuit to a series circuit. We saw the series circuit, and then we worked backwards through the original circuit. And the series circuit will help us to solve the original circuit. So we kind of do the same thing, but in AC, they deal with something called a block impedance. A block impedance. And all that is when you look at the AC circuit, depending on the way the circuit is drawn, it should be clear that certain things are in series and certain things are in parallel. So if you have several things in series, you can combine that into like one entity, one block. Or if you have things right next to each other in parallel, you can combine it into one block. So just to reduce the complexity of the circuit, they'll show the circuit as a block, then they'll solve what's in the block. And it's easier for me to show you than it is for me to say. So let me show you what I'm talking about. I put this up on Blackboard, I think. I hope I did. But this is the series parallel example I got for you. If I didn't put this up on Blackboard, I will. I'll just write it on but I think I put everything up there. I upload everything for every class at one time. Sometimes I forget what I put up. I need to check before class. But I was in Hamilton, Ohio today, right before class. I had to get here, try to get logged on.
What is that? The series parallel?
Yeah. Was it up there?
It's on there, yeah.
Okay. Thank you.
No
So the series parallel, I'll put it over. Well, I guess I'll put it over here. We don't need it. So here it is if you didn't download it. We have a resistor. We have a capacitor. We have an inductor. It tells us the resistor is 1 ohm. It tells us this is 3 ohms. And this is 2 ohms. They give us this over here, 100 volts, angle 0 degrees. So they give us that, and the first thing they want us to do is says redraw the circuit using block impedances. So what is a block impedance? Well, all a block impedance is just, this is the simplest series parallel circuit you can have. So you can imagine me giving you something way more complicated than this, but when you're trying to teach a principle, you do something simple, and then you advance it, then you move towards the complex. So your eye should naturally be drawn to this right here. This inductor and capacitor are in parallel. So what a block impedance tells you to do is to think of these two as one unit. One unit. We're going to just call it Z2. And think of this as a unit. Now, that resistor is by itself, but if I had another resistor in series with it, I could just put a box around that as one unit. So we're going to call this one Z2. Or Z1, I'm sorry. So this is what we mean by block impedance. It's just a block. You just draw a block around things that can be naturally grouped together. And the way you do it and the way I do it, if we had a more complex circuit, it might be different. It doesn't matter. It's just a way to again, simplify the circuit. So now what I'm going to do, I'm going to redraw the circuit with just the blocks, and I'm going to solve for what's in the blocks. So I'm going to redraw the circuit like this. Right, so there's my simple series circuit. Now, notice that this node right here, actually got the node, this connection point right here, is actually right here. These two block impedances. So now what we do is we solve for what's in the box. Well, this one, there's no solving. I can just look at it. This is, in polar form, this right here will be 1 at an angle of 0 degrees. And in rectangular form, it's just 1 plus J0. So I'm just going to write it as 1. Now this one, we got a little work to do. What I have is, I got 2 parallel reactances. So I got to do 1 over XL plus 1 over XC. Or, remember, I can treat this just like I would do a problem in DC. In DC, I might not, with these easy numbers, it might be better to use a product over the sum rule. So I can do whatever I can do in DC, I can do in AC. So I can say Z2 is equal to XL times XC over XL plus XC. That's probably the easier way to do it. If I do it that way, I get 3 times 2 over 3 plus 2. Now, these angles, let me put my angles in there. I'm getting kind of messy. Really what I should have written was 3 at an angle that's at 90 degrees times 2 at an angle of minus 90 degrees. And then we're going to add these down here. So this will be 3 angle 90 degrees plus 2 angle minus 90 degrees. Well, right off the top, you know, when you add these, you really want these to be in rectangular form. You don't want them to be in polar form. So this in rectangular form is a J3, and this will be a minus J2. So I'm going to change that to a J3 This will be a minus J2 if I convert it over. So on the top, when I do my math, multiply those complex numbers. 3 times 2 is 6. If I add the angles, I get 0. Divided by, if I take J3 minus J2, I get just 1J. So that 1J, now I can convert it back to polar form. It'll be 1 at an angle of 90 degrees. Convert that over. And then when I divide it, I get 6 at an angle of minus 90. So this box right here, that's something you can read. When I write the box, so you have to go through some work to get this box, but by just looking at that part, covering up the rest of the circuit, it kind of hides the complexity. To me, I think it's simpler to think about it that way. But anyway, we got 6 angle minus 90. And if I write that in rectangular form, it's just a minus J6. So I got 2 block impedances. I'm showing the value of the opposition in both polar and rectangular form for all the block impedances. So under that part of the problem where he says, first redraw the circuit using block impedances, that's what you do. That's number 1. But then number 2, find ZT in the simplified circuit. That's this. Well, that's easy because all I have is a series circuit over here. So I can find ZT all night long. I just add them up. So let's add these up. Let me get rid of this. ZT, total impedance, it's just going to be Z1 plus Z2. The reason I wrote both rectangular and polar, so I just got it at my fingertips. I know if I'm adding, I'm going to use rectangular. If I'm multiplying and dividing, I'm going to use polar. And so I'm adding, so I'm going to use the rectangular form. So Z1 is a 1. Got a 1. And this is a minus J6. So there is my total impedance. Now, right away, when you do that, get used to showing that both ways. Show it in rectangular and polar forms. There's our rectangular form. I'm gonna convert it to polar form. And well, you guys got to do it. I didn't calculate this one. I'm just doing this kind of off the top of my head. So I need somebody to convert this over. Now we're in quadrant what? We're in quadrant 4. So the angle you get back is the right angle. Remember, it's the correct angle. Is what I'm saying. If you're in quadrant 2 or 3, you got to add 180 to the angle. So far, we've been either in quadrant 1 or 2, so you guys have been lucky. Here we've been in quadrant 1 or 4, so you guys have been lucky. And here again, we're in quadrant 4. So somebody do the Pythagorean thing on this. Tell me what the value of that is, and it's a polar number. I guess I'll write it over here. And if you convert that over, what do you get? I don't know what else. Let me see. While you guys are converting that, let me see what else we're supposed to do next. Well, we're supposed to do power, go right into power, but I didn't upload the sheets yet. So we'll do this problem and we'll have an early day today. And I'll upload the power documents and we'll spend, now we're probably going to have to spend a little time. I'd like to get it done in one day, but we probably won't. Anybody convert this yet?
Got a 6.08 at negative 80.5 degrees.
We'll stick that over here, 6.08 angle. All right. Number 3, find the total current. Well, we made it really simple now. Find the total current. So we got the total impedance. I'm going to find the total current using Ohm's law. So my current phasor is equal to my voltage phasor, which is 120 angle 0, divided by my impedance, which is 6.08 angle minus 80.5 degrees. What's 120 divided by 6.08?
$19.74.
Okay, thank you. So there's my current. I got 19 amps. Now, just like you would do in the circuits 1 class, what you want to do is right away you want to show the currents. Guess I'll use this blue. Show the current in each circuit. So my total current is 19. We could have rounded. Because it's 19.74 angle 80.5 degrees. Over here, I'll do the same thing. My total current was 1974 angle 80.5 degrees. So I show my current. So now you can probably guess what he wants you to do. You got the current and want you to find the voltage across basically all of these. So to do that, what you'll do is find the voltage across Z1 and Z2. We got everything we need right here to do it. It's just let me write it down just so you can keep writing your notes. So find Z1 voltage drop, Z2 voltage drop. So V1 is just IT times Z1, and V2 is just IT times Z2. So let's do the math here. We said this was 19.74 angle 80.5 degrees, and Z1 is just 1 at an angle of 0 degrees. So when I do the math there, I can get my voltage drop. I guess I'll use green for voltage. Oh, it's going to be really confusing. I don't have any more colors. All right. I'll tell you what I'm going to do. I'm going to change these to black. And then I can use red for my voltage calculation. So if I multiply this times this, I get 19.74 angle 80.5 degrees, and that would be volts. From here to here, So over here, I write the same thing, 19.74, angle 80.5 degrees volts across that first element. So I found my voltage. And then we do the same thing for V2. So V2, I got my same current because it's a series circuit. I got 19.74, angle 85 degrees. I'm going to multiply that by Z2. Now, since I'm multiplying, I'm going to use that one. It's going to be 6 at an angle of minus 90 degrees. And I'm leaving the units off. Amps, ohms. What is 19.74 times 6? How much is that?
At 118.44.
Okay, and what is that? Minus now, is that minus 9.5 degrees? Okay, so that voltage, I can write that as, let me make some room. 118.4 angle minus 9.5 degrees. So here's this voltage. Here's this voltage from that point to that point. So over here, Z2 came from things in parallel, so I know I have that voltage across both those elements. I'm going to write it in between here. This is 118.4 angle minus 9.5 degrees. But that voltage is across both those elements. So now the only thing I have unsolved is the current through the capacitor and the current through the inductor, but that's a piece of cake because I got voltage across each element. I got the ohmic value of each element. I can find the branch currents. So that's all we have left to do is the branch currents. Let me see. He tells us to find VR, VC, and VL. Well, of course, this is VR, and VC and VL are in parallel, so they both get V2. And then he tells us to calculate IC and IL. I knew that was coming. So let's do that. Calculate IC and IL. At this point, we're done with this circuit, so I really can erase it because this just helps us solve that one. So I'm going to get rid of that. We can calculate IC and IL. All right, so if I do that, IL is just going to be V2 over XL, and IC V2 over XC. And those are all phasors, so I write it like that. So I got 118.4 angle over this is the L, so that's 3 angle 90. And then this one is the 118.4 angle minus 9.5 over 2 angle minus 90. All right, so what's that? Half of 100 is 55.4. So we get 55.4 angle, shoot. It'll be what? What's 90 minus 9.5? Why can't I do that in my head? 89.5? Is that right?
Isn't it 80.5?
80.5, isn't it?
80.5. I told you. 80.5, all right. But it would be Yeah, positive. You said 80.5? And this would be, that's this one, so that's that. And then, did you get this one for me? Actually, that was that one. We got to do that. Which one did we just do? We did that one. No, it was this one. We did that one. This IC, because that's half of that. And then, yeah, okay, so we need IL. So give me IL. 118.4 divided by 3 is what?
I got 39.6.
All right, so the angle minus 99.5 degrees. And this comes. So we will consider this problem solved. The whole point is just to emphasize the block impedances, and how easy it makes the problem. It kind of just hides the complexity. All you're really doing is it's forcing you to look at one part of the circuit at a time. But that's a really good way to think about it because there's so much going on here. Converting it from this form to that form. This is a really good way to do it. This comes from a book that I used in college called Boylestad, which to me is the best book ever written on circuit analysis. The problem is they keep coming out with new editions, but Boylestad has been dead for decades. So I don't know how he keeps writing these new books, but some kind of way he does. We got a couple more on here to do though. He says, calculate the power delivered to the circuit using, this time he gives us another equation to use. Remember I squared R? It says, what effect does XL and XC have on the power delivered? So he wants us to calculate the power delivered to the circuit like this. Power delivered is equal to I squared to R. Now we can do that because remember the only element in an AC circuit that dissipates power is the resistor. And the ideal circuit is the resistor. So I can calculate the power using this form of Watt's law. Now this I squared R, this should be IR squared times R. And well, that's the total. So my magnitude of that is going to be 19.74 amps. I got to square that, and I got to multiply that by 1 ohm. And that'll give me the power dissipated by the resistor. So somebody do that for me. 19.74 squared is what?
390.
So there is my power delivered. That's the power dissipated by the resistor. And then the last question says, they didn't ask us to find the power factor. Oh, yeah, they did. No, it says, what effect does XL and XC have on the power delivered? The answer is reactive components cannot dissipate power. They have absolutely no effect on the power delivered. The only thing that can dissipate power, the only thing that can change electrical energy to heat energy would be a resistor. And then the last thing they want us to do is find the power factor. So power factor is just the cosine of theta. So I got the cosine. Now the angle, if I draw this as a phasor, my phasor diagram, I see my voltage is 120, it's at 0 degrees. So my voltage is at 0 degrees, it's sitting right here. That phasor is sitting right here, it's B hat. And the current is out front. It's out front at 80, about 81 degrees. So the current is over here. It's like this. That's I hat. That's the total. So if you look at those phasors and they spin around, you're going to see the current phasor, then the voltage phasor. So in this case, the current is leading. All the other cases, it was lagging. So to get my power factor, I'm going to take the cosine of 80.5 degrees. If you take the cosine of 80.5, tell me what you get.
Uh, 0.17.
And then the way you write that, if you just on the quiz, is wrong. You'd be mad at me because you think you should get partial credit, but I won't give you partial credit. You got to say 0.17 leading. It's leading. And that's the complete answer. Now notice what we said before, that what we want usually is the power factor to be closer to 1. So if it's closer to 1, that means my circuit is more resistive. If it's closer to 0, that means it's reactive. Well, that's way down there. That would be not good. So next time we get together, we're going to talk about AC power. And I'm going to show you how you can do something to the circuit to get that number up. It's called power factor correction. And that would be it's kind of an involved calculation, but it's all simple math, trick stuff. So that's really it. I don't have any more. You guys have any questions, comments, concerns, anything you want to talk about? Okay. I don't know if I put the other lab up. Did I put another lab up yet or not? The other lab, I think, is just looking at the O-scope video. And then, I don't know, we're going to have to go up to the school because I don't really know how to do anything without the O-scope. So you guys might as well just plan on it. You got to come up there and you're going to have a mask and all of that. I've already told the dean, or I told the technician to tell the dean, so there's really no way around it. I can give you we'll do just a couple labs this semester, but you have to touch the oscilloscope. We got 2 types. You got to do something with both of those. So what I may do is just put a couple labs up that you guys can just work ahead on, and then when we need to go up to the school, we'll pick a day. Actually, it's just a process getting into the school. They gotta take your temperature. You gotta have a mask on. It's a whole bunch of stuff you gotta go through. So I'll get that set up, but I'll put up the next lab here. I'll try to do it today if I haven't already done it, but I'm not going to promise it. But by today or tomorrow, I'll put it up and see what else I can give you guys to work on. If you want to look at the book, I would say find some practice problems on either series, parallel, or combination circuits. I don't really like the way your book does it. I don't think the problems are, I just don't like the feel of the problems in the book. I'll try to come up with some out of my book, but I could scan the chapter and give you those. That might work. I'll see. I'll think of something. But if you guys don't have any questions or comments, it's nice outside, so enjoy some of that good weather out there, no humidity. And I will see you on, today is Wednesday. I will see you on Monday. Have a good rest of the day, guys.